Okay, let's start the class. We are going to talk about the global explanation. What is a global explanation? What we talked about in the previous class is a local explanation. That is, given the machine a photo, and the machine will tell us why it thinks there is a cat in the photo. The global explanation is not targeted at a specific photo to analyze, rather than examining the model we have trained and found out that, according to this model, what does a cat look like? What does a cat look like according to the network? For example, suppose you have a trained convolutional neural network to be examined. You know that there are many filters and convolution layers in a convolutional neural network. Inside the convolutional layer are a bunch of filters. Then you take a picture as the input. For the convolutional layer, what is its output? Its output is a feature map, and each filter is a metric. Now, suppose we have a picture as the input to this convolutional neural network. We represent the picture as a capital X. Because the picture can be represented by a matrix, we use the capital X to represent the matrix formed by this picture. When inputting the picture to the network, you will find out that the feature map in a certain filter, for example, the filter 1, has relatively large values. What does that imply? That might imply that there are many features in image X that is in charge of the filter 1. There are many patterns in this image that the filter 1 is responsible for detecting. When the filter 1 sees these patterns, the output value of the feature map has a larger value. However, what we are going to do is the global explanation. We don't have the picture, image X, yet. We don't want to analyze any specific picture. We want to know what kind of patterns that the filter 1 interests. How to do it? We can create a picture. It is not any specific picture. In our database, the machine finds it out by itself. We are going to create a picture that contains the patterns that the filter 1 can detect. By looking at the content in this picture, we can know what patterns the filter 1 is responsible for. How to find this picture? We assume that each element in this feature map of filter 1 is called Aij. The feature map of the filter 1 is a matrix. We use Aij to represent each element in the matrix. What we have to do now is to find a picture X that is not in the database. We treat this X as an unknown variable. Treat X as trainable parameters. Our goal is to find a picture so that the feature map we get by feeding this picture into the filter has the values in the feature map, which is Aij. To be the larger, the better. We need to find an X that the sum of Aij, the output of the filter 1, has a largest possible value. We use X star to represent the optimal X we find. It is not any specific picture in the database. We treat X as an unknown variable or a learnable parameters to find out this X star and feed the X asterisk into the network that is trained beforehand. The convolutional layer of this network outputs the values of these features. The value in the feature map it outputs will be as large as possible. How to solve this problem? You will use a method similar to gradient descent. As we are going to maximize something, it's not gradient descent. Rather, it is gradient ascent. Its principle is the same as gradient descent. Okay, after finding out the X star, we can observe this X star to what kind of features X star has. We can also know that Y X star can maximize the value of this filter map and know what kind of pattern the filter 1 detects. Here is the result of an actual operation. We use the MNIST dataset. MNIST is a dataset of handwritten digit numbers. We use MNIST to train a classifier. Give it a picture for this classifier. It will judge which number it is from 1 to 9 in this picture. After training this classifier, we will take a look at the filter in the second layer of the convolutional layer. Then we find the corresponding X star for each filter. So now, every picture below is an X star, where each picture corresponds to a filter. So you can imagine that the first image is the pattern that the filter 1 wants to detect, and the second image is the pattern that the filter 2 wants to detect, and so on. Okay, from these patterns, what can we find? We can find what the second convolutional wants to do is indeed to detect some basic patterns. For example, something like strokes. From these images, you can see that Some of the pattern here wants to detect the horizontal lines. And this filter wants to detect oblique lines. This filter wants to detect the pattern of straight lines. Each filter has the pattern it wants to detect. You know that since we are now doing handwritten number recognition, the numbers here are made up of a bunch of strokes. So the job of each filter in convolutional layers is to detect a certain stroke. And this phenomenon is very reasonable. Okay, so then you might think that, what if we are not looking at a certain filter, but to see the output of the final image classifier? Can it? What kind of phenomena will we observe? Considering the output of this image classifier, we try to find a picture X to make the score of a certain category higher. Because we are doing the number recognition now. Y consists of 10 values corresponding to 0 to 9. We choose a certain number. For example, if you choose 1, then you want to find a picture which makes the score of class 1 at the output of the classifier as higher as possible. If you use this method, what phenomenon can you observe? Can you see the numbers from 0 to 9? After you actually do it, you will find that you can't. This is the result you may receive. For example, this X star can make this image classifier have the highest score on class 0. This picture can make your classifier get the highest score on class 1, on class 2, on class 3, and so on. You will find that you actually observed a bunch of noise. You can't see the numbers at all. From these results, you might think it's amazing. If you don't know the adversarial attack, here, the machine sees a bunch of noise. Does it believe it sees numbers? How could it be so stupid? But we have taught adversarial attack. I guess you won't be too astonished. When we were doing adversarial attack, we already told you that you can let the machine see all kinds of objects by adding some strange noise on the picture, which is invisible to human eyes. So for the same reason, the machine doesn't need to see a picture that really looks like the number 0 to classify it as the number 0. If you give the machine some messy noise, the machine can also classify it as 0, with also a high confidence score. Actually, if you use this method, which tries to find a picture that maximizes the certain output for a certain category, and you want to see what this machine imagine of what an object of the certain category looks like, it may not be that easy. Like today's example, the example of handwritten number recognition, you are just looking for an image that maximizes the confidence score of a certain class. If you simply do this, you will only find lots of noises. What is the correct way to do it? Suppose we want what we see today is a number that is more like people's imagination. What should I do? When you are solving this optimization problem, you have to add more constraints. For example, we have some imagination about this number. We already know what the numbers might look like. We can add the limitations we want to this optimization process. For example, we are not looking for an X that maximizes the score of yi, but to find an X that makes the scores of yi and r of x greater at the same time. What does this r of x mean? This r, x, is to measure how similar this x is to a real number. For example, the numbers are made up of strokes. So, a number doesn't have so many colors in the whole image. Plus, though the image size is big, there are only a few strokes in it. So in the whole image, there are not that many places with colors. We can treat this as a constraint. Just put the constraint into the process of finding x. During the optimization, we hope to find a x that are more like numbers. If you add some additional constraints, for example, we want the white dots to be fewer. In this constraint, it hopes that the white dots are as few as possible. Suppose we add a constraint that makes the white dots as few as possible. The result we see will be like this. It still doesn't look like a number. But, if you look closely at the white dots, it do look like something. For example, this looks like 6. This looks like 8. If you want to really get something much like a number. Or suppose you want to get the results like what's in the literature. Many people in the literature will say that he uses some method like a global explanation to infer what an animal looks like in an image classifier. For example, if you look at the following document, it tells you that it has an image classifier. It uses the method we just mentioned. It can infer what this red-crowned crane looks like in the image classifier, or what a beetle looks like. Looking at these pictures, they are really similar to red-crowned cranes. You can see that. There's a bird. There is a red-crowned crane. It has a foot in the water. You can really see the beetles in these pictures. But to get a picture like this is not as easy as you think. If you look at this document carefully, you will find that, to get these pictures, you have to add a lot of constraints. You have to add a lot of constraints based on your understanding of images and what an object should look like. It also needs a lot of hyperparameter tuning. You know, when we solve the optimization problem, we also need to tune the hyperparameters, like learning rate. So after putting lots of constraints and tuning a bunch of parameters, you can get this result. So this result can't be made easily. If you want to see a very clear picture with the global explanation method just mentioned, here is a trick that uses the generator. You train an image generator. You have a bunch of training data, which is a bunch of images. You take this bunch of images to train an image generator. For example, you can use GAN. You can use VAE. We have taught GAN, though we have not taught VAE. Anyway, what VAE does is to train an image generator whose input of image is a low-dimensional vector sampled from the Gaussian distribution. The low-dimensional vector is called Z. After passing it into the image generator, its output is a picture X. We use G to represent this image generator. For the output picture X, we can write it as X equals G of Z. How should we use this image generator to help us infer back to a certain category that the image classifier imagined? For example, for a certain cat, what would the cat category or dog category it imagines look like? You can connect this image generator and this image classifier together. The input of this image generator is a Z, and the output of it is a picture. Then, for this image classifier, we use this picture as the input, and then it outputs the results of the classification. In the previous slides, we claimed that we are looking for an X to let a certain dimension in Y, which is a certain category, get the highest possible confidence score. Then, we call this X as X star. Then, we just saw that, by doing this, you can't achieve good results generally. Now, with image generator, the method is different. We are not looking for X now, but we are looking for a Z. We are looking for a Z that generates X through an image generator. Then, we throw this X into the image classifier to generate Y. We hope that the certain category that Y corresponds to get the highest possible score, we are looking for a Z to produces X, and to generate Y. We expect the bigger the Y is, the better the results will be. Then, this Z, which can make Y the bigger, the better, is called Z star. After finding out this Z star, we throw this Z star into G, which is the generator, to see what the image X star it generates looks like. Okay, what does X star look like? Suppose you want to produce an image with the highest confidence score for ants. These are the photos that came out. They are great, right? I can immediately see that this is an ant. Let's do this again for volcanoes. We generated a bunch of volcano pictures and picked out those pictures with a high score with a classifier. Here are the images. These images look like volcanoes indeed. You might think that this whole idea is a bit of a stretch. If the picture you found, for example, the ant or volcano picture, is different from what you have imagined, you blame the explanation method. You would say that the explanation method is good only if the picture corresponds with your imagination, even if the machine is forced to do so. Perhaps the picture looks like noise to the machine. Maybe the number it imagined looked like noise to us. But we are unwilling to agree with this fact. We invent new methods and force the machine to produce a picture that looks more decent. The recent explainable AI technology often does this. We don't actually care about what the machine really thinks. We don't even know what the machine really thinks. We want results that people will be pleased to look at. After you've done that, you tell everyone that this is what the machine thinks. Then your boss, your customer, will be very happy after listening to your results. Recent explainable AI techniques tend to do this. So we talked about two mainstream techniques of explainable AI, which are local explanation and global explanation. There are many other techniques. For explainable AI, though, for example, you can use a relatively simple model to imitate the behavior of a complex model. If the simple model can imitate well enough, you analyze that simple model. Maybe we can know what the more complicated model is doing. For example, you have a neural network. Because it is a black box, if you throw a bunch of X in, say, a bunch of pictures, it will give us the classification results. But we can't figure out its decision-making process, because a neural network by itself is very complicated. However, we can generate a simpler model, a more analyzable model, like a linear model. To interpret the results, we train this linear model to imitate the behavior of the neural network. When the neural network is given x1 to xn, it outputs y1 to yn. We ask this linear model when given x1 to xn, it also has to output the same y1 to yn as the black box. We ask this linear model to imitate the behavior of the black box. If the linear model can successfully imitate the behavior of the black box, we can then analyze what the linear model does. And it will be easier to do analysis. After the analysis, maybe we can know what this black box is doing. Of course, there may be lots of questions here. For example, can a linear model imitate the behavior of a black box? We talked about it in the first lecture. There are many problems that only neural networks can do, while a linear model can't. So what the black box can do may not be able to be done by a linear model. That's the truth. In this series of work, there is a particularly well-known one called Local Interpretable Model Agnostic Explanations. Its abbreviation is LIME. This method didn't claim to use a linear model to imitate all the behaviors of the black box. It tells you right in the name that it is local interpretable. The linear model only needs to imitate a small part of this black box. Because the capabilities of linear models are limited, it is impossible to imitate the behavior of the entire neural network. But maybe if we let it imitate the behavior of a small area, we can interpret what happened in that small area. That's a classic method, called LIME. If you want to know what LIME is, you can watch the video below. We won't go into the details for now. We also have homework related to LIME. It is up to you to read some paper by yourself and get a feeling of what LIME is. Okay, so that part was an introduction to explainable machine learning. Let's see if there's any student asking questions online. So, I can see everyone's questions. Hold on. Someone asked if it would be better if we add a class that represents none of the above, and try to minimize the probability of that option. Let me try to understand your question. Suppose we've trained an image classifier, and it's a classifier for digits. Your question is that if we add one more option to the classifier, and that option represents the input we passed in wasn't a digit at all, would the result be any better? I have never done a similar experiment. In practice, if we're using the MNIST dataset, there may be a small problem. Because every image in that dataset is a digit. Every image that we're dealing with is a digit. On the other hand, suppose we actually collected some images that are not digits, and added another category that represents not a digit. Now, what would happen if we input an image and require the classifier to believe the input image is a digit while trying to minimize the probability of the not a digit category? I haven't actually tried, so I can't come up with a good answer at once. But, judging from the success rate of adversarial attacks nowadays, I think it's still very possible to find an image that doesn't look like a digit, but the network thinks it's a digit, and the probability of not a digit is low. I have never tried it before. You can try it yourself and see how it turns out, if you're interested. Okay, is there any question? I know that the live stream is not exactly real time. There may be few minutes of delay between you and me.